Don't want to work out details. I want to, yeah,
Yeah, no, yes. Oh, yeah. So, like,
Yeah, but it's easier if there's someone watching.
yeah. If you just let me know, then I can.
I'm already in the
You want that?
I wouldn't talk about
Those are probably by definition. So you're free.
All right. We're going to get started soon.
Have a great time.
We have spreadsheet, but you can import so you can build, but then.
All right. Welcome back, everyone. Let's continue. I'd like to thank Mike for the very kind words at the beginning of the talk. So I did not know of this semi-secret talk by Daniel Spiegel. I've seen a few talks by him, so I'm sure he explained this stuff much better than I did. But yeah, I'm very happy that it generates some interest in my work. So it's a great pleasure to be here among these, to talk about this stuff that I'm interested in among these distinguished speakers. I kind of have the opposite problem that Mike had. So I understand the quantum spin system reasonably well, at least I like to think so. But for the topology side, it's much more difficult for me to understand. So these kind of workshops are very useful to try to talk to each other and try to understand what's going on. We're interested in the same things, but just coming from a different perspective. So yeah, I also would like to thank the organizers for giving me this opportunity. It's been great so far. Right. So just as Bruno said this morning, I will also have to think what I promised you earlier this week, what I would tell later in the lectures. So I try to remember, and hopefully everything is in this final lecture, which will wrap everything up. Right. So what we've done so far, well, we constructed these superselection sectors. We defined the monoidal product. We defined well, we had a way of decomposing the monoidal product into direct sums, and in some cases these are a decomposition into irreducibles. And we defined the braiding, of course. It was sort of the main goal. There's one more further piece of structure that I want to mention here, namely that of duality or rigidity. So in our case, we can, because we have these star categories, we can sort of formulate this in a sort of symmetric way. So I say, if I have an object in my category, I say a conjugate for R is a triple with another object, rho bar, and two morphisms, rho and rho bar, such that well, this R is in this home set, and R is in this one, and we have these so-called zigzag equations. So I didn't draw a picture here, but if you draw kind of like this graphical calculus, you see like these things are called zigzags. But yeah, so let me give you the physical interpretation of these things. So these are so-called conjugate charges. So this, for example, so what this means is that if I fuse my rho bar with a rho, it contains a copy of the trivial sector. So this is really meaning if I fuse these two things, I can go back to the vector to the trivial sector. That's essentially what this captures. So having this kind of properties on the category or structure, we can define something that's called the quantum dimension. So it kind of gives you a dimension on on these sectors and lots of other interesting stuff. So in the case of the Tor code that we've been considering, we have these conjugates. Actually, all these things are self-conjugate because they square to the identity, so that's easy to see. And in many of the other models, we can explicitly construct them. However, I'm not aware of any results that sort of give the existence of these conjugates. So I know in so where you don't know, where you cannot construct them explicitly. So I know in algebraic common field theory, this is guaranteed under some conditions, like for example, one-way covariance, satisfying other conditions. But in our case, it's not known. But you can also make examples again in quantum field theory, where such a dual does not exist. Right. So in many of these, in sort of the in this sort of algebraic description of anyons, often this is kind of postulated that we have this kind of conjugate. So it would be interesting to see if you can actually find some conditions that guarantees this.
Sorry, so how I understood the last lecture is that in your approach to DHR, like in the Tor code, there are huge representations that don't have duals, but you don't count that as a counterexample, right?
So these are kind of so this indeed would be an example if you take like infinite direct sums, they would not have a dual. But that's sort of for kind of non-interesting reasons. So that will be the counterexamples will be sort of this kind of infinite type. Yeah, that's
It can get worse.
Yeah, but good. There's one more question that I want to address. So I constructed these examples of sectors in the Tor code. So I had 4 of them. And then I developed this theory to get this whole structure of this whole category, and that were much more generally. We just needed a few assumptions. So a natural question is, of course, for the Tor code, are there maybe any other representations that satisfy the superselection criterion that I somehow didn't find yet? And that's what I mean here with completeness. Right. So there's the different ways that you can approach this question. And maybe if I have time, I'll do another one, but this is maybe the nicest one here. So maybe just to restate the question. So we constructed 4 of these irreducible sectors, and are these everything? And the answer is yes, and it follows from this result, recent result by Algebras and Sidnat. So this result is more generally for all quantum double models for a finite group G. So we can consider the Hopf algebra based on the group algebra, the quantum double algebra based on the group algebra of G. So this is a nice quasi-regular Hopf algebra. The representation theory of this algebra is very well understood, and you can classify the irreducible representations of this algebra by pairs of a conjugacy class of G and an irreducible representation of the centralizer of an element in the conjugacy class. So you just pick an element in the conjugacy class, you look at the centralizer, so you get a group, and you take an irreducible representation. So these pairs, they classify the irreducible representations. And for each of these irreducible representations, you can define what in their terminology is called an anion sector. So for me, an anion sector, so what it means in my terminology is just an irreducible representation that satisfies the superselection criteria. So for these models, they can construct these. And these representations are pairwise disjoint, so that means they are not equivalent to each other. Pairwise, they're pairwise inequivalent. And any anion sector or any irreducible superselection sector of these quantum double models is unitary equivalent to one of them. Right. So in the Tor code, G is equal to Z2. So well, there are not so many conjugacy classes in Z2, and irreducible representations of the centralizer. So yeah, you can easily see that there are only 4 different these irreducible representations. So indeed, we have found all of them. Good. So let me say a little bit more about our category now, and this is kind of like the conclusion of this whole construction for the Torah code. So we have this quantum double that I just mentioned. This is a moderate tensor category. So here again, this is kind of like related to the point that came up a bit earlier. You really want just to look at the finite dimensional representations for kind of trivial reasons. So the irreducible representations are a one-to-one correspondence that I just mentioned in well, on the previous slide. So what we can show is that this category delta DHR, where this F superscript now is just means that I only restrict to taking finite direct sums of these objects. So finite direct sums of the irreducible ones. So equivalently in this case, you can restrict to all the basically the subcategory where the morphism spaces are finite dimensional. And you can see that this is closed actually on the tensor part. So that's one way of avoiding this sort of trivial examples where you take infinitely many copies of the same thing. Right. Good. So yeah, this category is very tensor equivalent to this representation category. There should also be an F here. So yeah, it preserves the braiding and all the other structures basically that we're interested in. So this means that our anyons, all their algebraic properties are completely described by this representation category, or representations of this quantum double, as expected. Right. So maybe a sketch of the proof. It's probably hopefully it's more or less clear now, but you can just fix a certain cone. You can choose your representatives in this cone, and then you define a functor sort of in the obvious way, because by construction these sectors, they are, well, you can see it here in the theorem, they're related to this irreducible representation, so it's clear what you should send, what to where. You check that this preserves the braiding. Again, because we can calculate it explicitly, that's just a small check that you have to do. And then because everything is up to unitary equivalence, you can basically map everything to this code. So that's sort of the proof sketch. We basically calculated all the structure already explicitly, and you just have to check that they match up on both sides. Good. Yeah, so that's so yeah. Basically, this shows that we built up this whole theory that works quite generally, and it gives us the right answer in the examples that we actually can do explicitly. So that's always very encouraging.
I have a question.
Yes.
So also with respect to have a twist on the category, it's actually
Yes.
the recon category plus the sum.
Yes.
Modular, it's actually modular in addition.
Yes.
So do we get this from this formalism of DHR?
Yes, you can also get the other structure. Yeah, so I didn't talk about it now, but you can also get it. Yeah, twist and all these other things. So it's a bit more than just greater tensor. Yeah, so there's a bit more structure that I'm not going to go into now for lack of time, but you can basically find the whole thing. Yeah. Good. I want to say a little bit about the non-abelian case. In particular, this is work together with my former PhD student Madi Hamdan, and together with Algebras and Pieter Naajkens that I mentioned already earlier. So I mentioned this before already. You can define this variance of the historic code for any finite group. Actually, any suitable Hopf algebra. But then the question is, of course, can you do the sort of the same analysis for finite groups? If G is abelian, the analysis is very similar to the Torah code, apart from, well, you don't get 4 sectors, but you get group squared sectors. So yeah, there's more different kind of path operators, but otherwise it's very, very similar. For the non-abelian case, it's a bit more difficult, and let me just explain why. and sort of give you the main idea of what kind of things you have to change. Right, so instead of these path operators now, so before I only had to care about either paths on the lattice or paths on the dual lattice. So if you look at the non-abelian model, you need to have what's called ribbon operators. And these are sort of a combination of a path and a dual path next to each other. So you get, instead of just a single small path, you get a slightly wider ribbon. So you can basically, yeah, so that's you need to sort of treat these things together instead of separately. Right, so that's not too important. So the main features are still the same. You have these so-called ribbon operators that create excitations. If you act with these ribbon operators on the ground state, then the state will only depend on the two endpoints of the ribbon, and all these things that we had before. We can decompose them, so you can cut them and write the result as in terms of smaller ribbon operators and so on. Right. So one of the main differences, however, is that as we've just seen, our sectors, our irreducible sectors, should correspond to irreducible representations of the quantum double. Right. So if G is non-abelian, there are irreducible representations that have dimension bigger than 1. And if that's the case, we don't have a single ribbon operator associated to this type of representation, but they come in multiplets. So namely, given the number of ribbon operators is given by the dimension. I mean, the ribbon operators from a linear space, and the dimension is given by the dimension of this irreducible representation. And in particular, they're also not unitary anymore. So we cannot just conjugate with these ribbon operators to get an automorphism or something like this. So we have to do something a bit more clever. So it turns out it's easier to, instead of defining a map from A to A itself, it's easier to construct so-called n-prime morphisms. So we take a morphism, a star morphism from our algebra into this amplification. So we just the D by D matrices with entries in A, and D is the dimension of this irreducible representation. So essentially, what you do is you arrange these multiplets of ribbon operators in a D by D matrix, and then you conjugate with this matrix. So instead of conjugating with a single ribbon operator, we conjugate sort of with a matrix of ribbon operators. And this will give you a star homomorphism from there to there. Right. So that doesn't quite fit in our framework. You can do the whole define the whole analysis in this kind of way. That's kind of like a natural analog of how to define fusion and things like this. But the other thing that we can do is we can actually map this back into endomorphisms of our auxiliary algebra. And this is again where we use this properly infiniteness of the cone algebra. So essentially, we can realize this D by D matrix algebra on the big Hilbert space by just using these partial isometries to cut the big Hilbert space into T different things. So, right. So that's so then we are back in the original endomorphism setting. The disadvantage of this is not explicit anymore. So on the C-star algebra, we can actually calculate everything explicitly. For this step, you would have to use some isometries over which you don't have much control, so you cannot really calculate things explicitly anymore. So the idea is you analyze this category on this side. You show that it actually gives you the same thing as doing on the the structure that I got before, and we obtain the representation category as expected. Right. So maybe I should say one more thing before going on. So in this case, these maps are really going to be endomorphisms. So in the Tor code, we defined automorphisms instead of endomorphisms. And it turns out that this really has to do with these things being abelian anyons. So if you have abelian anyons, they will be described by automorphisms. If they are non-abelian anyons, they will be described by endomorphisms. Good. Right. So that's sort of the extension of this work to sort of non-abelian models. I would expect you can do this for the general quantum double models or for Hopf algebra. But yeah, basically every step becomes more and more complicated to work out these things explicitly. So it should work in very much the same way. It will just get much more tedious. Right. So there's still a few open questions that I sort of mentioned. Well, some of them at least before. That some of them I will go there now. So I already mentioned the one about conjugates, and I think I also mentioned this, but it's good to repeat this. So if rho has a conjugate, it automatically follows that the dimension of rho is going to be finite. And as I argued yesterday, this means we can always decompose it into irrationals. Right. So I will not say much about that because I don't have much more to say about that. But I will come to the first question. So is this category indeed an invariant? So as we've heard many times, we're interested in the classification of phases, and until now I've only considered one single state all the time. Right. So I maybe want to mention some other questions. I don't think I'll go too much into there. But some people asked me this also outside of the lectures. An interesting question is, what kind of categories can we actually expect? So we've already had the question, is this category going to be always modular? And the answer was basically I don't know, but this does seem to be the case in everything that we've considered so far. But I don't have any physically meaningful conditions that would guarantee that if I define this category substrate cycles that I actually do get something modular. So that's an interesting question. There is something you can write down in terms of the intertwiners between T-now sectors that guarees that the braiding is non-degenerate, so which is kind of like the main part of modularity. However, this condition there's not really an interpretation for what it means, so it's not very useful in practice. And it's also not something that you can easily show. So yeah, so I think really one of the sort of the main open problems is which states lead to an interesting superselection sector theory. So yeah, so there are different kind of axiotizations that you can try to find for these topologically ordered models. So this LTQO is already mentioned by Bruno. We have sort of a variant of this where you can also look at boundaries. I think Dave Pennies will talk a little bit about this next week. But yeah, this is still very far from a complete answer to this. But I think it's an interesting question. I guess sort of the main issue with all these things is that although our approach is quite general, you don't really need much. You need a high duality, which we believe holds quite generally, and you just need a superselection criterion. But if you actually want to find for a given theory, for a given state, if you actually want to find superselection sector theory, that's of course very difficult. And basically the only models that we can handle so far are these kind of commuting projector Hamiltonians, which are somehow easier.
Peter, can you comment on the first bullet point invariant?
I will come to this. That's going to be the next part of my talk. So I will try to explain that. Yeah. So yeah, I will call this stability. So we have already heard a little bit about this from Bruno. So I'm going to give some sort of informal definitions because so I want to define a sort of an equivalence relation of states. It's very similar to what Bruno explained earlier. It's really motivated by that. But yeah, so if you really want to get sort of all the technical details here, I don't really have time for that, and I don't think it will be too insightful here. So I will try to sort of paint a general picture chat. And if you want to find the details, we can look here at Yoshiko Ogata's paper. Right. So what I'm going to do is I'm going to look at automorphisms of my quasi-local algebra that I will call approximately factorizable. And so what does it mean? Well, for any cone lambda and any delta bigger than 0, we have these two conditions. I will show a picture on the next slide. It's maybe a little bit more clear what this means here, but we should be able to find automorphisms of a lambda, being lambda, and so these two for a lambda, and similar for the complement of this, and then automorphisms capital Psi acting only near the boundary of lambda. And now I'll show you in a picture what I mean with this informally. And unitary is V such that we have this equality. So this should be a tilde instead of a hat. But essentially what I want to do is I want to write my automorphism as a tensor product. So this only acts in the cone, this only acts outside of the cone. And then alpha is equal to that, up to some kind of perturbation near the boundary, and some unitary. And this unitary, I should have written this down, this unitary should be in the quadrilocal algebra. So that's important. And I want the same to be true for the inverse. Good. Right, and I don't want just any unitary, but I want to be able to approximate this unitary with something that's localized in cones. So that's essentially the idea. So let me give a picture. That's probably more helpful. So I have this cone lambda here, and I want to write my automorphism as something that acts only inside the cone here. So that's I call beta lambda, something that acts outside of the cone. And then this automorphism capital Psi acts kind of like near the boundary here. So I want my picture is not great because this thing should be of course inside of the cone. So I want the outside of the cone to be at like a slightly bigger angle. So the further you go out in the cone, like the wider this fit gets, and I want the same be inside the cone. Right. So that's kind of the first condition. And the second condition is that I have this. So I have this unitary here with which I have to conjugate. And if I take a slightly wider cone than lambda with the same apex, and I will move this cone out along the center line. So again, my picture is not great. This is supposed to be in the middle of this thing. So yeah, you just have a slightly wider cone and you just move it out. And I want to be able to choose my unitaries Vn in these cones, converting to this V. And I want this conversion to be sufficiently fast. And in Bruno's lectures, we have seen how we can sort of quantify what sufficiently fast means. So that's really the thing you should think of.
Can you show the previous slide again?
Yeah. Yeah. So I really I want to write my automorphism as something that's acts. Yeah, that's acts sort of like kind of like a product inside the cone and outside of the cone. So it sort of acts independently there, up to some kind of a perturbation around the boundary of it.
What's the role of this delta? Where does it appear?
All right. Yeah. Sorry. Yeah. That's a good point. So this delta is a parameter that kind of controls the angle of this cone with respect to the other one. So if this has like the opening at angle phi, then this grating has opening angle like phi plus 2 delta. I believe. That's yeah. So that's yeah. So yeah. So you want to be able to sort of to choose this thing, and of course you can expect if this opening angle is sort of smaller, then maybe its convergence will be a bit worse. The main point is that you should get a good handle of that. Right, so this looks maybe a little bit like a convoluted definition, but this is this is essentially what's necessary to show the stability that I want to talk about. But maybe an important question so where do these come from? So this is so these are a generalization of this sort of finite death quantum circuits that you may be heard about. But you should really think of this framework that Bruno talked about today. Of this, for example, with this Hastings generator exists. So they will give automorphisms that satisfy these properties. Right. So maybe some slight technicalities there, but I think in general that's a good tool. So in particular for us, what will be sort of the relevant use case is suppose we have some gapped local dynamics satisfying these local topological order conditions. I also don't have time to specify what these are, but they basically tell you that locally your ground state is kind of like an error collected code. So it's all models like the Keith Diab model like this. Right. So what you can do is you can so we have this Hamiltonian, there's a spectral gap in the GNS representation, and we can perturb this with some small perturbation. And if this perturbation is sufficiently small, then this new Hamiltonian is still gapped. And the ground state of these things, they are related by an approximately factorizable automorphism. So as it is stated here, this is a combination of results by Pieter Naajkens and Pieter Naajkens and Zorak. So they prove that if you have these conditions, the spectral gap stays open for sufficiently small perturbations. And then a result by Bachmann and by Bruno, Pieter Naajkens and Sims shows that you can actually connect these ground states with the automorphism. So Bruno explained as to in his lecture earlier today, sort of a generalization of this result that's more widely applicable, but it's the same idea. So and as Bruno said, you can really find so the way I stated, we are only interested in this automorphism, but if you use this theory, you actually get like a whole path. So this is really related to the physical, well, the definition you see in many physical papers that Bruno also mentioned, that you have kind of a path of Gax Hamiltonians. That's the way we should think of. Good. So now we can say what do I mean with the phase? To be two states to be in the same phase. So this should say two pure states, but say in the same quantum phase, if there is such an approximately factorizable automorphism alpha such that these results. So this is essentially the same definition that Bruno gave. And so what do I now mean with my category being an invariant? Well, I mean, right, I have these two different states. I can, if my conditions are satisfied, I can define this category of DHR superselection sectors. Is it the same category or not in the same phase? That's the question. So is this really an invariant of this kind of phase?
You mean same category to equivalence?
Yeah.
Equivalence, Braiders, monoidal.
Braided monoidal equivalent in this case, yes. So yeah, stronger than Morita equivalents. So. Actually, they're all modern, so it's probably the same. Right. Good. Right. So we have some issues here now, because I have this this alpha, this automorphism. In generally, it does not map a cone algebra into a cone algebra. Right. So that would be the case if both of these are the identity, but in general, that's not really the case. So this means that, I mean, first you might think, okay, yeah, I just have some automorphism of my algebra, I compose its automorphism, it should preserve everything, right? That's kind of like a natural guess. It's a bit more subtle because our category very much also depends on the von Neumann algebras that we look at. And if you compose this representation with the von Neumann, if you compose this representation with this automorphism, you need to look again at this cone von Neumann algebras, but a priori it's not clear how these new von Neumann algebras are related to the original ones, for example. So the representation can change very much with this outer boxes. And in particular, it's not clear anymore because these cones are not generally not mapped into cones. You cannot transfer Hague duality from pi 0 to a Hague duality of the perturbed model. Right. So Hague duality is usually something that's I think it holds quite generally, but it's not easy to prove. So yeah, and especially if you start perturbing things, it's there's basically no hope of proving this directly. So what we want to do is we want a weaker notion of Hague duality, and this is called approximate Hague duality. Right. So this is the definition here. Again, I will show a picture on the next page. So representation pi 0 of A is set to satisfy approximate Hague duality for cones. If for every cone and every parameter epsilon is small enough, there's some unitary. So now the unitary doesn't live in my quasi-local algebra, but it lives in the representation space. And some R depending on actually on the cone and on epsilon as well, such as this holds. Right. So the component of everything outside of the cone is contained in this algebra. So maybe I should explain the notation here a little bit. So with this, I mean I take the cone and I translate it along the axis over the distance r epsilon. So I kind of pull it back along the axis. This subscript epsilon means I make my opening angle slightly wider by the angle epsilon, or 2 epsilon, I guess. And then I finally have to conjugate with the unitary. So just say maybe this states so if you have Hague duality, then this would be equal to, well, this R. So this will be 0, this will be 0, and this would be identity, and this would be equality. So that would be Hague duality. Sorry. So in particular, anything that satisfies Hague duality satisfies approximate Hague duality in a trivial way. Right, so that's the condition. I mean, we need one more thing, similar to before. Maybe we want to be able to approximate this unitary with unitaries in these cone von Neumann algebras that I defined. So I take a cone and I look at the corresponding von Neumann algebra, and I want to get the error in this approximation going to 0 fast enough. So again, I can fix this cone and I can move it back to sort of cover the whole space eventually, and so I get bigger and bigger regions for which I can approximate my unitary, and this approximation should go to 0 fast enough. Right. Sorry, this the picture should have come before. But this is the picture that we have. We have this cone lambda. We have this cone, well, slightly bigger cone that's obtained by translating this lambda and then opening the angle a little bit. And then the commentant says, yeah, we are in this bigger space. So what it really means is, if you have this cone lambda here, you take something outside of there, then with approximate Hague duality, if something commutes with everything outside, it would be localized in this cone. Now with the approximate Hague duality, it's not localized in this cone anymore, but you need to take a slightly larger cone, and you need to conjugate with this kind of unitary. So maybe this is a good point, sort of to say informally what these unitaries actually are all about. So if you look back at Bruno's talk, so this locality of these automorphisms that come from these time evolutions, this is very much controlled by this Robinson kind of bounds, and there we have sort of this exponentially, typically exponentially decaying tails. And essentially, what these unitaries do is they kind of sweep up all these exponentially decaying tails and put them kind of right back in the cone. That's essentially what's happening. Right. Good. So now we have this approximate Hague duality, and this is actually enough to develop a superselection sector theory, very much along the same lines as we did before. So everything where we use Hague duality, we now have to use approximate Hague duality. So the superselection criterion, that does not change. You look at the same kind of representations. My auxiliary algebra will now have a slightly different definition. Namely, here I take now, before I took the cone algebras, and now I take the commutator of this thing. So by Haag duality, these two things are the same thing. I don't have Haag duality anymore, so now it's easy to work with this one. But essentially, the idea is still from this approximate Haag duality, you still get that you can approximate things in cones. That's very important. Right. So before we essentially we identified that we can see our representations satisfying the superselection criterion as representations that act trivially outside of the cone. So this will not be true anymore. So instead of acting trivially outside of the cone, you still have this decaying tail. So it'll look like the identity, but only up to some error, and this error goes to 0 the further away you are from the cone. But the important thing is, that's where we use approximate Haag duality. The image of these representations still ends up in our auxiliary algebra. So before, the whole point of defining, the whole idea behind defining our monoidal product was that we could get something of an anamorphism of auxiliary algebra, and this is still the case. So we can show that it ends in here. Right. Same is true for the intertwiners. Again, you have to do some kind of approximation, so it will not be in a cone anymore, but it will be approximated by things in cones, so approximated as well. And because this is, this is the direct limit of these kind of things, if you can approximate things with things in a cone, then the result will be in this algebra. Good. What's probably the most complicated difference in this whole procedure is the braiding, right? Because when I define the braiding, I relied on the fact that if I move these two cones away from each other, they act non-trivially on different regions, which means I could interchange them. Right, but now we have this exponentially decaying tail, so they don't act non-trivially anymore. So you would have to do a bit more carefully. And essentially what you will have to do is you have to take, you still move the cones into different directions, but then in addition, you have to move the cones to infinity. So you have kind of a limiting procedure. So you can define sort of a limit of these operators and show that this limit will define later. So I would say that the main ideas are the same, but now of course there's much more analysis involved, and you have to be very careful doing all the estimates right. So that's why I will not go into too much detail here. But this is now the important result. So that's so maybe I should actually say that I should have said it before, but this definition of approximate Haag duality, it's really what you get if you take one of these quasi-factorizable automorphisms and you apply them to original state, and you can ask to something that is Haag duality, and you can ask, what do you get? And this is what you get. So that's where this comes from. But good. So what's the result? So suppose you have two uniformly bounded finite range interactions with pure gap ground states. And suppose we have one of these automorphisms that connects these two ground states. So this is the setting that Bruno also was talking about before. Then if one of them satisfies approximate Haag duality, the other one will also satisfy approximate Haag duality. Did I mention this? Yeah, sorry. I skipped this slide because I wanted to show my picture. But yeah, the point is that this approximate Haag duality is stable. So if I have something that satisfies approximate Haag duality, I apply my automorphism, then the new thing will also satisfy this. Right. Good. So yeah, if one of these satisfies approximate Haag duality, then the other one will do so as well, which means I can define these DHR categories in both cases, and they are unitary Boyd-Mann equivalent. So indeed, it is a invariant of the sector. Right. So as Bruno mentioned earlier, you could define phases without reference to any Hamiltonians. You can state the similar theorem here. So the only reason why I specify the interactions here is because these conditions, they will give you that these cone algebras are properly infinite, and you get this partial isometries that you can do the define the subject objects in the direct sums. But yeah, so if you just if you have some other way of proving that your state has these properties that are properly infinite and as these projections that are unitary, that are equivalent to the identity, so well, that you can define sub-objects, let's say it like this, then the statement is true. So this is only, this first bit is only needed to guarantee that that you have the structure. Good. There's also another paper by Bruno's former students, Matthew Chia, and myself and Bruno, where we kind of use a slightly different approach to prove something similar in a less general setting. This is the most general setting. Good. So that's one thing that I think I promise you that I will prove. I want to say, come a little bit back to this question of when do you actually get an interesting superselection sector theory? So I want to give you a sufficient condition, sorry, a necessary condition. Right. So I want to explain this concept of long range entanglement, and this Toric code model has long range entanglement, and that's essentially why we can have anyons in the first place. So I'm going to define what I mean with the product state. So I'm going to define a product state with respect to a cone. So if I have a pure state and I want to have states on my cone and outside of my cone, and then of course look at the product state. And I want my state to be quasi-equivalent to this, or unitary equivalent. Doesn't really matter. So maybe just to say, so this is a weaker notion of what people usually say with the product state. Usually people say product state in this context, they mean it's a product state with respect to each of the sides individually. For us, for our purposes, it's enough that that's a single cone for which this is product.
So this tildes mean what
exactly? Yeah, so this is quasi-equivalence.
Okay, so it's actually weaker, but not only unitary equivalent.
Yeah. So it's a slightly weaker notion of equivalence. That's enough. Right. Good. So what we can show using this is if you have a state like this, then you can look at the GNS representation of this cone, and it's going to be a type 1 vector. So it's going to be isomorphic to B of H for some Hilbert space. And because it's a type 1 vector, we automatically get Hague duality for this given cone. I mean, this is a sketch of the proof. We actually give a different proof in our paper. That's a bit more precise, but essentially the main idea is here. Because you have this type 1 vector, if you have a type 1 vector, you can always get a tensor product decomposition of your Hilbert space in such a way that, well, my cone algebra acts on this first tensor vector and as the identity on the second, and the same for the conjugate F. And because my representation is irreducible, it follows actually that the weak notion must be this whole thing. So this algebra is this. And then if you take commutants, so if you take the commutant of this von Neumann algebraic tensor product, it's the same as taking the commutant of each of these things. So here you get the identity in here, P of H and the complement, which is precisely this. Good. So yeah, so these states are quite nice.
Yeah. One question here. So here the
Yes.
assumption is that omega also satisfy Hague duality condition.
So if you have a state like this,
it's automatic.
then it satisfies Hague duality at least for this given cone. Yeah.
Okay.
Yeah. That's because it's a type 1 vector. Right. So what's the result then? So if we have a pure state which is a product state with respect to some cone, then the sector theory, if we define the superselection sector theory with respect to the state, this is actually trivial And in this case, what I mean with trivial, every representation satisfying superselection criterion is a direct sum, possibly infinitely many copies of my representation. So I only have just to recall, so I would use this as my reference representation. The reference representation was sort of the trivial anion. So this says that in this situation, everything is a direct sum of the trivial anion. A very quick proof sketch. So by the superselection criterion, we can localize a representation pi that satisfies the superselection criterion inside my cone. Then, by what we've seen before, we get an endomorphism of my cone algebra. Right, because my cone algebra is type 1, and type 1 algebras don't have so this should be a normal endomorphism, so continuous with respect to the so with respect to one of these topologies of the phenomenon algebra. But yeah, so a type 1 vector does not have any interesting non-trivial endomorphisms, so that's basically how the result was. Again, we gave a slightly different, more explicit proof in our paper, but this is essentially the main idea. So I want to make some maybe some remarks here. So the first one is we only need omega to be a product state with respect to a single cone, so it doesn't need to be with respect to all the cones. Nevertheless, the superselection criterion, of course, must hold for all cones. So that's kind of already taken care of, sort of. So yeah, so it's that's why it's always enough to have a single cone, because you can always move everything in there and then do the analysis there. And it's important that omega is pure, which implies that rho lambda is a vector. So if it's not a vector, you can get into interesting stuff. Let me not say too much about that. Right. So now I can define what long range entanglement is. So a state omega is said to be long range entangled if this if I compose it with one of these quasi-factorizable automorphisms, I cannot get a product state in the sense that I just defined. Right. So that's essentially So you cannot transform the state into a product state. So that's essentially the definition that you always also find in the literature. Of course, our definition is quite technical because we need this quasi-factorizable thing. So it's maybe not the most general definition, but it's the one that we can make work. But yeah, the corollary of the two previous results is that, so the first one is that if we have these product states, we get a trivial superselection structure, and the second one is, well, the superselection structure is invariant under applying these quasi-factorizable automorphisms. So the conclusion of these two things is that if omega is not a long range entanglement, then we have a trivial entangled, then we have a trivial superselection structure. Or in other words, we need long range entanglements to actually get something non-trivial. Good. So let me see.
A question. Yeah.
Yes.
Is this quasi-factorizable automorphism is also the same as a so-called finite depth local unitary circuit?
Yeah, so I think so. A finite depth unitary circuit should be an example of such a thing. Yes, you maybe need some condition on the unitary is not growing too much in support if you go out. But yeah. I think yes, I think that's yeah.
Or more generally, this automorphic evolution to the rapidly decaying Hamiltonian.
Exactly.
An example.
Yes, right. Yes. So basically all the things that Bruno or they called LGAs, for example. I think Anton usually calls them like this in the papers. So they're all similar ideas. Yeah.
Just because you're a little bit quiet, I wanted to ask that question myself. So an LGA is quasi-factorizable?
I don't want to say this in this generality, but morally speaking, it should be. But yeah, there's maybe some technicalities that you have to check.
Okay, thank you.
Let me see how many. Okay, I have. Let's see. So yeah, that's. I think that's what I want to say. Yeah. So maybe I think I have time to do this. So before for the quantum double models, I mentioned this complete list result that kind of gave us a complete list of sectors. I want to give an alternative approach. So I quite like this one because it relates to subvector theory. Right. But yeah, so the result that I mentioned earlier by Bols and Van Necker, this really depends on a good understanding of the underlying diagram. So I want to give a different approach here. So this is based on an idea that works very well in rational conformal field theory, and that we can adapt to ours. So what we're going to do is we're going to take two disjoint cones that are sort of away from each other. I can also show pictures soon. And I want to choose them such that there's a vector, a type 1 vector, n sitting in between them. Well, not in between them, but in between one and the commentant of the other. So this is so-called split inclusion. So this is the distal split property or approximate split property. You can show that this holds for quantum double models. And what I can do is I can define two von Neumann algebras. Maybe just go to the picture because it's a bit clearer. I have these two cones, so I want them to be far enough away so I can find this type 1 vector. I can look at the von Neumann algebra generated by the cone von Neumann algebra for this cone and for this one. So that's what this V symbol means here. It's the smallest von Neumann algebra containing both of these. So the von Neumann algebra generated by these two things. Right. So this von Neumann algebra sits into a bigger von Neumann algebra. Namely, you take everything outside these two cones, and you take the commentant of this. Right. So of course, with one cone and Hague duality, this commentant will be the same as the cone. But now we have two different cones, and in general, these two algebras they're not the same, even if Hague duality holds. Right. So we always have this inclusion by locality, but they're not equal. And from irreducibility of a representation, it follows that these two things are actually factors. And what you can also show is that the relative commentant of the small algebra into the big one is proportional to the identity. And so what we have here is what's called an irreducible subvector, the operator algebra architecture. Right. So my claim is that this R hat algebra is actually bigger than this RAB in general. So let me try to explain why it actually is bigger. So what you can check if you have two morphisms, rho A and rho B. So rho A is localized in lambda A, rho B is localized in lambda B, and I have some unitary intertwiner between them. So I have some. I can take something in rho A and then I can transport it to rho B. That will give you this V. And then a short calculation. It's very similar to before. So I did this calculation with Hague duality, showing that that this intertwiner is in this cone algebra. If you do the same calculation a bit more carefully, you can see that it's actually in this algebra. Right. I should have said this in before, but I'm back in a setting where I assume that Hague duality holds, so not this approximate version. Actually, you don't need it for this, but yeah. So, but in general, this V is not in this two cone algebra. So maybe if you go back to these pictures that they had before, where I defined this intertwiners as limits of these parts, you recall that we had to go. Well, we had two different. You can think of these two different parts and two different cones, but to go from one to the other, we had to sort of cross these cones, go into space in between there. So these operators are not obviously they're not going to be in this commentant of this. Right, so that's not a proof that they're not in there, but that maybe gives some indication why that's the case. You cannot approximate these things by just things in the cones. Right. Good. So the idea is this R hat is bigger because it contains intertwiners. So if you can somehow quantify how much bigger it is compared to the small algebra, you might learn something about how many of these intertwiners we have. Right. So then, fortunately, we can do this because there's this thing called the Jones index. So Jones defined it for type 2-1 factors, but it was later extended by Longo and Kozaki, for example, to general factors. So yeah, so this what it does is it assigns a number to this subfactor inclusion. It's always bigger than 1, bigger or equal than 1 with equality, so equal to 1 if and only if these two algebras are the same. And for us, the important part is if this thing is if the index is finite, you can really see sort of the big algebra as sort of a vector space over the small algebra, or what you want. So there's some finite remaining vi in the big algebra, such that every element in row AB can be written as a linear combination like this of these elements. So this bi are fixed. And the number of them is controlled by the value of the series. Right. So what's the result now? You can prove that the number of sectors is bounded from above by this index. So what you just because we should be able to localize in any cone, we can just take the infimum of this number over all pairs of cones that satisfy this condition that I mentioned earlier. And this will give you an upper bound on the number of sectors. If each sector has a conjugate, we can define the dimension function, and we actually have this sharper bound, or this better bound, more useful bound in terms of the dimensions. But the main point is for the ability on the double models, we can actually, sorry, this equation is not right. We can actually show that row hat AB is equal to a cross product of row AB with some group action. So that's a well-known subfactor. We know what the index of these things is, so it's just the index of the group here. So it's gives you 4 in the Torah code. We already had 4 different sectors, so by this argument, this means that must have been all. Right. So I kind of like this one because it involves subfactor theory. However, it's not really obvious if you can even generalize this to sort of this approximate eigenvalue. So this thing is not obviously stable. Of course, you should get the same thing because the categories are the same, but yeah, I'm still quite fond of this. Right, so let me give you a very brief summary. So the main point is, so we can obtain this Brady-Caesar category of subselection sectors from first principles from the local dynamics. So the local dynamics really only came in selecting the reference state, and we needed very few assumptions, namely this approximate eigenvalue and the ground state cap. I'd like to think of this as a sort of a simple way of getting the superselection sector category, but I realize I've already been talking about this for 4 hours, so it's not really that simple, but maybe elegant. But I like this. It tells you in principle what you have to do, and actually doing it's of course a different matter. But yeah, so we can identify the anyons with representation satisfying this criterion. We can construct explicit examples, and I think really one of the strengths of this sort of approach is that we can really rigorously prove that it's actually an invariant of the quantum phase at the same sectors. And I think the other interesting result that I mentioned towards the end is that this also shows that you need long range entanglements to get non-trivial sectors. So this really distinguishes it from the sort of the trivial, so from the invertible phase. Right, I've gone 3 minutes over time, I think. So thank you for your patience, and yeah, thanks for listening to this week.